Charming city, nice to talk here. So my talk is renormalization in discrete scale invariance in a classical diamond model. Most of the work I'm going to present is done with Sid Permeshwan, hopefully post soon, and it's based on some older work with Jerome, Steve, Sid, and Felix Flicker, who is now in Cardiff. So, and I will review sections of this, the older work as well, when necessary. One ground rule is that there are some proofs we have in our papers. I'm not going to outline them. I'm going to show pictures, and you have to believe me that they work, okay? Great. So just to set up the context of renormalization. So what I mean is, so imagine I have some square lattice with degrees of freedom denoted by this, represented by these blue circles. And let's say there is a Hamiltonian H0, which describes these degrees of freedom, and there is a partition function which is related to the Hamiltonian like this. When I say I want to renormalize, of course there are many schemes of renormalization. The one which would be pertinent to today's discussion would be real space block spin kind of renormalization. And so what I want to do is maybe like take blocks of 4 or larger number of spins, and I'm going to replace this blue degrees of freedom by some fat degrees of freedom, which are these brownish balls. Now, the RG transformation I will denote by the letter lambda, and what it entails is this probability distribution, conditional probability distribution. What it does is, given a set of degrees of freedom as 0, it gives you some coarse-grained degrees of freedom as 1. Right? And the way I set this up is you start with a partition function given in terms of S0, then you write it as a joint distribution in terms of both S0 and S1, which is given by this probability distribution. Then I marginalize over the microscopic degrees of freedom, and that gives me the effective Hamiltonian at the first level, right? And then I write down the new Hamiltonian on a coarse-grained lattice. Usually, when you do this for models, you expect that under this transformation, as you keep doing it again and again, the Hamiltonian flows, and it flows to a fixed point. Now, these fixed points, they could either sort of denote phases which are short-range correlated, or more interestingly, maybe they could denote phase transitions or critical point with infinite correlation lengths. Right? Typically, it's such fixed points which denote non-short-range phases where there are interesting correlations. They are characterized by some emergent symmetries. Maybe there's a continuous translation symmetries, typically rotation symmetries, and translation and scale invariance, right? So they're described by conformal field theories and things like that, as all of you know. So what I'm going to do today is I'm going to show a classical statistical mechanics model, okay, which has a fixed point, but the fixed point is not characterized by any of these familiar sort of symmetries and more interestingly, I think the scale invariance this fixed point is going to show, that's going to have discrete scale invariance. So I can only do the RG by some fixed set of length scales. The coarse graining is not over a continuous set of length scales, as I will show. The model I would be considering is a dimer model, and it's on a slightly weird graph. It's a quasi-periodic graph. And for those of you who are not used to thinking about either dimer models or quasi-periodic graphs, I'll try to do a short sort of what these things are. So first, let's see what a dimer model is, right? It's a simple classical model. So if I have a graph, dimers are these hard pink rods which stay on the edges of the graph. They're hard in the sense that the dimers can't touch each other. So each vertex has one sort of dimer touching it. You can maybe think of it as something close to Z2H theory with like the one dimer constant being something like a Pascal. Right? The graphs I will consider in this talk are going to be bipartite graphs. What that means is that the vertices of the graphs can be divided into two sets, like black and white here, and all edges of the graph connect one black vertex to a white vertex. Now, for all graphs, it's of course not true that you can have configurations where all vertices have dimers touching them. For example, this graph, you can't cover by dimers. All vertices can't be covered by dimers. This blue vertex here, that doesn't have a dimer, and these sides are what we'll be calling monomers. If it's possible to make a configuration which does not have a monomer, we say that the graph has a perfect dimer cover. And dimer covers are also called matchings because each dimer is like matching two different scales. So we could say it's a perfect matching or a perfect dimer cover. And you could also define maximum dimer covers and maximum matchings like this. So given a perfect or maximum dimer cover or matching, you could do all of these things. So for example, if you have two monomers, from one monomer I could find the alternating path. Alternating path is a path where each alternating edge has a dimer and does not have a dimer like that. So if I find alternating path and I flip the dimer occupancy state of all these paths, then the monomer moves from the beginning of the path to the end of the path. Right? So this is that's the question? No, sorry. So the monomer moves, right? If you have two monomers on opposite sublattices and I find the alternating path between them, and if I flip the dimer occupancy status of all links in the path, then I annihilate the two monomers. You can prove in bipartite graph theory that you can keep doing these processes, and if you keep doing these processes, you end up with the maximum matching or the maximum dimer cover. If you already have a perfect matching or perfect dimer cover, you could find these loops of alternating paths, and you could flip them, and by doing this, you could actually in planar graphs, by doing these processes, you could always go to all possible dimer covers. So this would be like an ergodic sort of move, which takes you through all these. Now, if you put this, and the statistical mechanics of these dimer models are basically given by a sum over all possible dimer configurations. There is no energy, typically purely entropic, and you can measure observables like dimer densities and correlations. In periodic graphs in 2D, typical periodic bipartite graphs, these things typically have power law correlations. They are described by a sign Gordon field theory in terms of some coarse-grained height variables. It's like they typically show posterior Thouless-like phase. But we are not going to consider this on periodic square and honeycomb graphs. I'm going to consider this in this sort of very weird.
Could I ask two questions about the easy case before you go on? You mentioned something that you don't penalize energetically the coverings that have the dot on them? Or
the monomers?
Yeah, the monomers.
Yes, so I do penalize. I'm always going to work with maximum matchings,
okay,
as many dimers as possible.
So you will drop those completely?
Yeah, exactly.
Okay.
So, yeah, I'll drop those controls. You could consider models where you put a chemical potential for those, but I will not.
Okay, very good. And also you said that these are related to like an XY model or something.
Yeah, yeah.
You said it has parallel correlations always?
On square and honeycomb lattices, yes.
Okay, just to me that seems really surprising because I guess there's no continuous symmetry. And you didn't
Or so basically you could, so you see there is this constraint, and then you could write it in terms of this sort of fields.
Yeah.
You know, some sort of curl fields.
Yeah.
And if you constrain those curl fields, it basically becomes a Gaussian actually. And,
I see.
And depending on the details of the lattice,
okay,
the Luttinger parameter is in the phase where the vortices don't proliferate, and it's like a XY phase. Basically.
I see. But I guess normally that has a continuous symmetry, right?
Yeah, it's emergent continuous.
Emergent continuous.
Actually, if you on bipartite lattice, you can direct arrows from A to B, and then associate like electric field. The dimer constraint is like Gauss's law, and this is like U1 in the electric system.
But doesn't it have monopoles which gap it out, which are relevant?
It is not relevant for the parameters of a square lattice. It's possible to find bipartite graphs or add interactions such that the symmetries remain the same, but monopoles proliferate. It's possible. But for square and honeycomb lattices, that's not the case. The Luttinger parameter is in a range, but the monopoles are not relevant yet.
Sorry, this is maybe. Oh, I'm sorry. So this is intrinsically two-dimensional classical.
Classical. It's not 2 plus 1. It's just 2D classical.
Okay, so I think that's the reason.
Yeah, they don't have to be
Basically,
relevant.
there are vortices and they're irrelevant.
Yeah.
Yes.
Thank you.
So we are going to be considering this on. We're now going to forget all about sign learning theory. Okay? So and we're going to consider the dimer model on this lattice. So this is called the Amann-Baker tiling. It's a tiling of 2D space using these squares and ROMs, and it tiles the whole space, but it's not periodic. So you can't shift this by any amount and make it follow each other. It's still ordered because you can eyeball it and see it's not completely disordered. If you Fourier transform and look at the Bragg peaks, then you'd see finite Bragg peaks. In that sense, it's ordered. And it's locally indistinguishable in the sense that there are many such tilings which are not related by translations to each other. However, any large patch you find in one, that can also be found in others. So it's locally, it looks the same. In that sense, it's locally indistinguishable. And then there are these large patches of 8-fold rotational symmetry. So there is a D8 symmetry which also shows up in the Bragg peaks. The way you make these lattices, okay, we are going to consider the dimer problem on this, basically. Sorry, I forgot about this figure. Okay. So the way we generate this lattice is by using these substitution rules, which are called inflation rules. So every time I have a square placket, I replace it by the smaller plackets. Every time I have a rhombus placket, I replace it by the smaller plackets. So this sigma is the inflation rule. So I will show you how to do this. So for example, if I start with this patch with a few tiles, I'll just use these rules here to do this, and I get a larger tiling. And I will again do this, and I will get a larger tiling, so like that. I could also consider the reverse process. I could start from here, and then I could get smaller tilings by putting these tiles back in. And this reverse process is called deflation. So if I go to smaller tiles, it's inflation, and this is deflation. Okay? So this is how the tilings are generated. Now, since these tilings are generated by these sort of substitution schemes, they intrinsically have some sort of self-similarity, which I'll tell you about in a moment. Now, there's one more thing I want to tell you, which is there are these 7 different kinds of vertices in this lattice. You can't have all vertices of all possible coordination number, and these names are given by basically the coordination number of the vertices. John Conway came up with the name for these things as emperors, because they have an empire. Like every time you have a 6 vertex, there is a certain configuration of tiles that always operate around there. It's not going to be particularly important for what we will let today. Now let's look at the scale symmetry, right? So if I take this tiling and let's say mark out all the vertices which are 8 coordinated, the ones which look like stars or flowers. Right? So these 8 vertices, they lie on the vertices of a larger Hammond-Benker tiling. So you see, what this gives me already is like a decimation transformation for the lattice. I've not yet talked about any Hamiltonian or any energy, but the lattice itself comes with these decimation transformations, that if I take the 8 vertices and remove everything else, the 8 vertices lie on the vertices of a larger lattice. So this is the decimation transformation sort of I'm going to use, really, to later build an RGB, but this is the transformation that the 8 vertices fall somewhere. Okay, so what I've already told you, that the Hammond-Benker graph for the lattice, at the level of the lattice, it has some sort of self-similarity, that the 8 vertices lie on a larger sort of tiling. And what I've not told you anything about is what the timer model does here. Now, you could put models like magnetism on these graphs. People have done this for 20, 30 years. And then what happens is those models really flow to the same universality class as periodic models. That's not somewhat interesting. Okay. So now the first thing to note is, if I look at a diamond model here, it's not so obvious how I would even construct a perfect or maximum diamond problem. Because usually if you have a periodic lattice, what I would do is I look at a local patch, I would put timers there, and then I would repeat this decorated patch everywhere. Here this is not possible because it's not periodic, right? So the way we go about doing this is first note that these 8 vertices, they always come with these sort of small local empires, which always have an odd number of sides. Now see, if you have an odd number of sides, there is no way I can cover it perfectly with timers, because each timer covers 2 sides. If I were to remove the 8 vertices though, then these local patches I could cover with timers. So to make progress on this, I first remove the 8 vertices, right? And then the rest of the graph I can show you. I can color like this. I've done nothing, I've just colored like this. So it decomposes into these stars and these things which I call ladders, these quasi-1D objects. These ladders, however, are built out of only these 2 motifs and nothing else. So now these 2 motifs I can cover by timers, and hence I can cover everything but the 8 vertices by timers. The problem is still not solved of covering the lattice by timers. But if I remove the 8 vertices, everything else I cover by timers. Now what I'm going to do is I'm going to try to match up the 8 vertices. Right? The 8 vertices now can be matched by finding out alternating paths between these 8 vertices and then flipping them. Initially it told you if I have 2 monomers, I could find out. So basically if I find paths like this and flip them, then all the black things would have timers, the brown things will go away, and now everything would be perfectly matched. But remember that the 8 vertices themselves, they make this lattice of the coarse grain graph. So matching the 8 vertices by finding out these alternating paths is exactly the same as actually matching up the Hammond-Benker lattice at a coarse grain scale. So the construction of the perfect matching can be iterated. I've reduced the construction of perfect matching on the microscopic graph to the construction of a perfect matching on a coarse grain graph like this. And I can keep doing it. And I can do it iteratively ad infinitum, and I can match infinite lattices.
Like to be like 100% defined, you can do it on a finite.
On a finite.
But with some specific.
Yeah. So on a finite graph, I could in the end have a O1 number of monomers.
Sorry?
Because on a finite patch of lattice, in the end I could have an order 1 number of monomers in the end.
Okay.
But this number is not extensive. So even if you give me 20,000 sites, I might have 5 monomers.
Okay, but
So-
you can. That depends on what
The boundaries and things like that.
But presumably you can choose nice boundaries.
I can choose
where,
nice boundary conditions.
Everything is fine, but you still have like 1 or 2.
Yeah, I could have like 1 or 2. And that depends on, so if you keep pores grading, in the end I would have a very sparse and small graph, and maybe that can't be perfectly matched in the end, that has 2 monomers. So, but the main thing is I don't have any thermodynamic monomer density, so in that sense. And I can always choose boundaries so that they completely go in. Good. So I've iteratively solved this. I've solved the problem of actually constructing a perfect matching, and I've done it using the discrete scale symmetry of the lattice. So maybe it points towards some effective matching problem of these regions around 8 vertices, because the monomer, the alternative paths go like this, and maybe it's effective matching problem. I'm not proven it yet. What we can prove though is that every 8 vertex, if I really look at a large region around the 8 vertex, they are surrounded by structures like these. So these things are membranes, and we can prove that in the perfect or maximum matching, these membranes exactly have 1 dimer connecting this whole membrane to the rest of the lattice. So these whole regions are things which we call effective vertices. The reason they're effective vertices is because the dimer constraint is effectively imposed on this whole thing. This hard Gauss law-like constraint that each site has 1 dimer going on top of it. That's imposed successively at larger and larger scales with all these regions. This whole red region has exactly 1 dimer talking to the rest of them. The blue region has 1 dimer talking to the rest of them, and things like this. Now, the way we prove this really is, so these are the effective vertices. Let's consider the smallest and simplest effective vertex. The structure is such that there are 9 blue sites and 8 red sites, but only the blue sites talk to the rest of the system. So if you were to have a maximum matching, only 1 blue site really is allowed to have a dimer connecting it to the rest of the graph. Because otherwise one of the red sites would be unhappy and you would have more monomers than you want. So the fact that I penalize monomers a lot, that's the thing which imposes the effective dimer constraint over this region. Now this is a simple sort of graph, and here I can show this. But these things also we could prove this, which I will not go over. Okay, right? So we have this effective dimer constraint. So basically now the hypothesis I would make, which I will prove in a moment, is that maybe at different scales this problem is the effective matching problem of these regions, effective dimer problem of these regions. So initially, of course, we didn't prove this. We really wished hard that maybe we have discrete scale invariance, and we calculated dimer correlations using using classical Monte Carlo simulations. And dimer correlations look like this. So this red triangle is, well, let's say I have a source dimer, and I look at connected dimer correlations. This sample has a linear dimension of about 150 edges. And you see that the dimer correlations are quite long range. Now this is logarithmic and it's a color plot, and color plots are known to lie under duress. So I can plot them on a real scale, right? So this is a log 10 scale, and I'm not going to try to tell you that these are power laws, but what I want to try to convince you is that the connected correlations of dimers, they're really slow. So there is some correlated physics happening across the lattice, right? Okay. So now what I want to do in the last 10 minutes or 12 maybe, because I started 2 minutes late, is that I want to try to construct explicitly RG transformation and show that this thing goes to a fixed point under the RG transformation.
Do you think we are power laws?
Sorry?
Do you think we are power laws?
I don't actually. I thought for some point, also I don't actually think they're power laws. I'll show you why. I think I'm now reasonably confident that they're not power laws. But also I don't think they're short range. I think since even at an emergent scale, I don't actually have any translation invariance or rotation invariance. I just have very complicated, slowly decaying functions which don't have that very complicated structure. I don't think these are simple functions, basically. Okay. I'll try to show you from the RG why I think so. Okay, so now let's try to construct the RG transformation. So let's say I have this and I start with a perfect matching on this lattice, right? So the black dimers are the dimers, and this is my macroscopic configuration. What I do now is I superpose another dimer configuration, but this dimer configuration matches everything except the 8 vertices. So I use brown color to do this, right? So I superpose dimers on this auxiliary graph, which just doesn't have the 8 vertices. Now in the superposed configuration of black and brown dimers, I remove all places where the blue, where the brown and the black overlap, right? So if I do this, I see from the overlap graphs paths which connect the 8 vertices, which basically lie on the coarse-grained graph. So every time I do this, every brown dimer configuration I superpose with a black dimer configuration, I actually get an effective dimer configuration from these paths of links connecting each other. Right? And of course, the exact effective blue fat dimer configurations I get, they depend on what brown dimer configuration I use. So the RG transformation I will define, it's defined probabilistically, where I sum over all possible brown dimer configurations like this. So the RG rule says, every time I have a microscopic dimer configuration S0, I sample using Monte Carlo the brown dimer configuration from the auxiliary graph without the 8 vertices, and then from the overlap graph, I construct the effective dimer configuration, which is the blue dimer. So this is my RG transformation.
And is the assignment to the edges unique?
The assignment to the edges is unique once I select auxiliary brown dimer configuration, otherwise it's not unique. Okay? So that's probabilistically chosen really.
But you made some choice of what you remove and what to look at.
Oh no, so that choice is unique, I think, because you could just start from here. So let's say this graph, I don't remove anything. So I start from this blue, let's say, and then if I follow alternating paths of blue and brown, it will always uniquely lead me to another dimer. I'm not, that removal is just so that it becomes easier to look at the graph. So the overlap graph of brown and blue dimers always has unique connections between the 8 vertices. Because in one of these dimer configurations, the 8 vertices are matched, everything is matched, and in another of these dimer configurations, everything but the 8 vertices are matched. So you overlap them, then of course the 8 vertices has to get connected to each other. This is the property of the transposition graph.
You always sample the brown dimers with a certain
Uniform probability now. Later they might get weights under RG, we'll come to that.
Because under RG, the weights are changed.
Yeah, they will get weights, I'll show you. I can calculate the weights as well, okay? Okay. So now, initially from the microscopic model, I sample the brown dimers uniformly, right?
Well, I didn't understand how in the coarse grain one, how do you decide there's a dimer or not?
Oh, so now, so let's say from this blue effective side, you can follow like alternate paths, like black, brown, and then if you go to a
oh, I see. Oh, sorry. If the path connects to two, then there's
a dimer.
But you made some background coloring.
And that background coloring I will sample over.
But what if, what if that path ended up being all over the world?
Oh, it could happen. Then this would be a bad RG transformation. You're right. That can happen. So I could do this for the square lattice, and it would be a horrible RG transformation. The path would generate long-range dimers. Here we generate very small long-range dimers. So it just so because I'm coming from this place of intuition that I constructed the perfect matching in a scale way. That's why it's a good RG transformation. It's not God-given. It might fail for the models.
But
yes.
I think the confusion is that, at least maybe this is the confusion. I don't see how you could even tell the output that, it seems to me you can only say there's a dimer on 2 neighboring sites.
No, but all sites have to be connected to something.
Oh, I see. You'll draw.
Yeah, I draw everything.
Sorry, I understand.
Right?
I understand.
But this your point is right.
Yeah.
It could go all over the world, and then it would be a horrible long dimer. Then the effective models are not dimer models. Like this would happen with a square lattice, where we know the effective model is something like a sine Gordon and not a dimer. But here they
your reference,
configure.
It's not fixed once and for all.
No.
You do something in addition.
Yes, the reference has to be sampled over.
You sample it over there.
So this is this, yeah. So the probability rule, it also samples over the distribution of the references here, really. That's a bit, I would say, not usual. But yes, we have to do it. This is, are we happy, shall we?
But mindful of the time, I think we should go on.
What's that, how much do you have?
You have, let's say, 8 minutes.
8 minutes, okay. I think that's fine. I'm here. So I already showed you how to construct the RG transformation. I will show that it leads to a fixed point. And then, if you have questions. So yes, so just to summarize, the reference dimer configurations on the graph with the 8 vertices removed, they have to be sampled over. So given a microscopic configuration, the choice of the effective configuration is not unique, it's only probabilistic. So I do this, and how do I test whether it works or does not work? I start with this reasonably small sample, maybe order 100 edges, and then I consider samples which are larger, but which coarse grain to this sample, right? I consider this series of things, And then I consider observables of this coarse-grained lattice for larger and larger samples. I consider reasonably large sizes. The largest classical sort of sample I considered had about 3 × 10⁻⁷ sites, which coarse-grained to this. And now, to show that they work, I first show the dimer densities everywhere. I'm really sorry to show you these ugly numbers, but there's no other way to actually convince you that the dimer density on all edges with RG transformation, they actually go to some sort of a fixed point. Now, this is just the dimer density, but I could also look at dimer correlations, right, which actually show that the distribution is invariant. I could also show dimer correlations. I've chosen a source edge really to show this data, but you could choose any source edge and you could measure correlations. And then the dimer correlations also to very good approximation, I would say. It goes to some fixed point. So what I've hoped to show you is that dimer correlations, dimer densities, they flow under RG to a fixed point. You could ask, okay, so what's this the effective Hamiltonian look like? What's the effective model? Okay, you can calculate things from this, but what's the effective model? I hypothesize the effective model. In the effective model, what happens is that the dimers just get some weights. So the partition function is, if you have a dimer somewhere, the partition function is a function of effective weights. What do the weights actually do? What the weights actually do is the weights really calculate how many such paths there are in some like weighted sense. Right? So if there are many paths to connect this to this, then the weight of an effective dimer here would be large. That's the sort of thing we're doing. Now, these weights can be calculated. It's a bit tricky, but I'll just try to go over it quickly. That's the last thing I'll show you. So the weights can be calculated within Monte Carlo, the weights of the effective dimers. The way I do it.
You can also introduce the correlations between dimers. You're not considering that.
Oh, here? Yes, I'm not considering that. I'm making this
Like the model is factoring.
here, right? Yes, yes. So see, the thing is, the way I will convince you that the effective model is a good model is by saying that the effective model reproduces all dimer correlations compared to when it's done honestly, you know. And also, I can actually calculate interactions and show that they're very small. So there is a way within Monte Carlo to calculate dimer interactions, and a posteriori I can check that this is a good approximation. It's a very mean field-like approximation, but it works for my case. The main contribution in RG is that the dimers just get renormalized weights. Okay, so the way I calculate this, I first consider this partition function, which is the sum of total number of configurations where I actually do have an effective number on a particular number of wedge. Given my hypothesis of the weights factoring, the partition function is given by this. You sum over all configurations such that this edge has a dimer, right? And then I consider an auxiliary partition function, which is just like this. However, by hand during the simulation, I put a dimer of weight 1 on this thing. So I just put a dimer of weight 1 on this thing and then I sample everything microscopically. The ratio of these two partition functions basically gives me the weight, right? So I just divide this partition function by this partition function. There are Monte Carlo tricks we could do to calculate those things, but this is how I calculate weight. It's a very mean field-like calculation in some sense. But then I calculate these weights, and I see that it reproduces again. It's a good sort of approximation to whatever the effective Hamiltonian is. In terms of these weights, which are the couplings, you can also look at the RG flow. It turns out that the weight of an edge, it really depends on the coordination number of the vertices the edge connects. So if it's edge connecting a 3 vertex to a 4 vertex, it has a certain weight, it flows somewhere. Right? That's what it depends on. I've done the calculation agnostically, I've calculated everything, and it turns out it's like this. So we have these weights, and hopefully, so basically, the story I'm building towards is how much time do I have left? 2 minutes, 2 minutes? 4 minutes. Oh, very good. So the story I'm building towards is that I have this model. It seems like under this discrete RG transformations, it goes to a fixed point. The fixed point Hamiltonian is reasonably simple. It's like a free Hamiltonian, except from the dimer constraints, which gives it all its non-trivial correlations. Now, the last thing I want to address is
why the 3-8 edge doesn't flow at the edge?
Sorry?
Why the 3-8 edge doesn't flow at the edge?
I think it's because of symmetry, and also, so it's because of symmetry, because this 3-8 edge is really this and this. It's the central edge, right? And we really normalize, because see, the weights are only defined up to some constant, and I normalize it with respect to this, really. That's why it's 1. I have to choose some normalization factor, right? Because I mean,
the other ones are very
sorry?
several of them that cannot fall.
It shouldn't be the case. So this is n equals 0. So I start with all dimer weights.
Yeah, but 3, 6, 3, 7, 3, 8, all do not seem.
Yeah, they do not flow. Right.
Oh, I see. 3.8 is normalization.
3.8 is the normalization,
But
yes.
the other one.
Yeah, so the other ones don't flow. I don't know if I can give you a more. Yeah, looks like they don't. 3.8 is the normalization. Yes, I don't know why the other ones don't flow. Very good. Okay. Maybe the local environments are similar enough that the counts don't change much. I guess that's the reason, but I'm not.
I mean, since nothing flows after n equals 2, right?
Sorry?
Is the
Yeah,
typical
but,
error-
and that's consistent with the result from correlations as well. The really, the main renormalization, and then it's almost in a fixed point. I'm just showing this to flex to some extent to see that we are really at the fixed point. But yes, yes, really. So I just want to convince you that this is the fixed point Hamiltonian. Okay. The last thing, you could ask me, how does the coarse-graining transformation look like? Does it look like block spin transformation? So what I've done is I've shown you connected correlations between the microscopic spins and the coarse-grained spins near a fixed point. And then, if then this is a coarse-grained dimer, then the correlations with microscopic dimers are a bit more nebulous than what you'd expect from, let's say, easy model transformation. So the same microscopic dimer really affects the fate of multiple coarse-grained dimers. I mean, what you'd expect usually in easy model is that if you have a block spin, then this small spin really just affects this big block and nothing else. Here it's a bit more nebulous. And that is what makes the fate of power laws very, very sort of. So just to show you, this is my last slide. So let's say start with the Hamiltonian like this. Right? These are the dimer variables and these are some magnetic field like couplings. Then the correlations at some level is given by this, right? This is the expression for connected correlation functions. And then the correlation at the next scale is given by this in terms of the next couplings. Now these two correlation functions in general can be related by this chain rule of derivatives. That I have derivatives with respect to couplings at some scale and I use the chain rule and write it as derivatives. So the main relation between these two things is this is the correlation function at the microscopic scale and this is the correlation function at a coarse-grained scale, and these are the derivatives between couplings. So what would happen if you look at a model of magnetism or a periodic model is that these derivatives, they go as b to the minus x, where x is the scaling dimension, and this gives you power laws, right? Typically what would happen is the only sort of non-zero derivative is the one within the block, and each of those would give you a factor of b to the minus x, where b is the sort of coarse-graining block length and x is the scaling dimension, and you get power laws. For us, these derivatives are very complicated. I'll just show you two derivatives. Like if I take a very small dimer here, the derivatives of all these places are finite. So so if I want to, at the fixed point, if I want to calculate the correlation between this dimer and let's say this small dimer here, that would be a weighted sum of correlations between all these links which are lighting up. And they are signed, so they can constructively or destructively interfere. And I think this is what really gives rise to that older sort of thing here. That's why they're not power laws, and the data is not bad, the error bars are really low. It's just that I think the functions are complicated. So that's basically what I had to say. That we seem to have found a discrete fixed point, which is basically it's neither quantum, and I think I've shown that it's probably not a path to a field theory. And yeah, so this is what I have. We could calculate some sort of exponents. Monomer weights are relevant, for example, and the couplings in terms of which I described the Hamiltonian there, irrelevant. I could calculate those, but things like that. But yes, that's my talk.
We're a bit over time. Perhaps one quick question if somebody has a quick one. Otherwise, you can ask Sounak. Going once, going twice.
I have one quick question. You started with a purely entropic model, and you ended up, I think, with the Hamiltonian with some non-trivial.
The weights are basically just by coarse-graining the entropy contributions of all small paths which lead to a dimer.
I see, but it's interesting. Is this a normal phenomenon that you end up with a non-trivial? It's like you can think of it as a Hamiltonian. Is that right? On the
Yeah, I guess. Yes.
Is that generic for?
For entropic models, I think this happens. Like you could think of just a dimer model on a square lattice.
Yeah.
The Lagrangian flows even if the starting model is entropic.
I see. Okay. Thank you.
Okay, so let's thank Sounak.
Thank you.